Now, given that you've taken up this challenge of explaining in simple words what really happens when you switch on a light and see the bulb, what we need to do this is a cell. Now, I have no idea what this is. I look at it, it's like some cylindrical thing. Something is positive, one is written over here. On the other side, there is something like a disk, some negative is written. Near what's positive, there is something like a small button on the top. How will I start here and understand how the light glows? What has this got to do anything with what I'm asking? Now, to do this, to really understand what a cell has to do with our initial question, you have to get a picture or an idea for what we call an electric current. Now, for some of you, it might be a new word, but let's see what it means. So, let's say you've seen a river, right, that's just flowing down a mountain, it's going really, really fast. Maybe in Haridwar, if you see Ganges, that's how it's going really fast. Now, you say that the water has a current in a given direction. Now, what it means is that if you put your foot in, you're going to get pulled in that direction. You can feel that current. Now, if you see that water going there, it looks smooth at this scale of what we're seeing. But if you really zoom in and you start watching, you see little balls of water. What make up water? There are two hydrogen atoms attached to an oxygen. It's okay. Just that picture is fine for you now. You don't have to understand it deeply. But you see all these balls banging against each other in random directions, but eventually having some direction they're going in. Kind of like if you're in a really crowded queue in Tirupati and you're getting closer and closer to the main deity. This is pretty much how it's going to look, a current of people. Now, if you replace balls of water with balls of air, which itself is a mixture of many, many kinds of balls, you get an air current, or what we call wind. But now, if you change scale, come back to some very real life objects, because all these are really small. Take tennis balls and put them in a pipe and let them all start moving in one random direction. You have a tennis ball current. Now, the question then for us is, what we mean by current for our purpose here is simply a large number of some kind of balls moving in some general direction as they are banging against each other. So it's time to test yourself. If I ask you now, if you know the current is in that direction, let's say a tennis ball current, then can you say that every single tennis ball at every single point in time is going in that direction? Can you even say that a tennis ball at some point should have gone in that direction? Think about it. Yes. The thing to notice here is, even though the current might be in that direction, each of the individual balls might be going in some random direction. In fact, if you pick one ball, it might be doing something like this, a zigzag motion, such that at no point it is actually ever pointing exactly in the direction of the current. So it is possible. So if you thought that the balls must also go in the direction of the current, you might have imagined the pipe to be containing balls that are beautifully parading like that. But in reality, you know that all we are saying when we say there's a current is that if you find a ball here, if you mark it, and then you look after some time, it will be somewhere over there. We are not telling anything about the actual path it's taking. You can take some random path like that. Never be exactly in the direction of the current. But if at some time you see it here, after some time, you can be sure it will be somewhere in that direction. That's what we mean when we say there is a current in that direction. Now, if I want to set up a current of tennis balls in a pipe that looks like a C like this, then I can collect one from below, I'll create a small gap, I push it back from the top, and I can keep doing this. And after a while I'll get really bored. I can hire somebody to do it. Let me hire a man who is trapped in a box, which has only two holes, one below and one on top. So I connect the two ends of this pipe to those holes, and I bury this whole thing underground. You're thinking, what are we even doing? And why are we burying this person underground? We'll talk about that. You'll understand why we're doing this. But for now, here's a man buried underground with only two holes, right? And he keeps picking up balls from the bottom part and puts it on the top again, below, and he keeps doing this all the time, thereby maintaining this current of tennis balls into the box and out of it. Now, this man is very hardworking, okay? He keeps picking up the ball, keeping it on top, thereby maintaining the current. But what if he gets tired and stops doing what he's doing? What will happen to the current of tennis balls? So if you watch what's happening, he's pulling a ball out, creating a gap, which is creating a gap on top, and then he pushes the ball back in over there. Now if he stops doing this after this, there's no gap created, there's nothing for anything to move. So all the balls are going to remain stationary. In other words, the current has stopped. Now let's take this man and put him under slightly different work conditions. Let's tell him, listen, the pipe is gone. Now there are some few balls below you. You carry them and do what you're doing before only. Carry one up and keep it up, but hold them there. So you're continuously doing this. After a while, he is holding a few balls on top, right? He has to do some work to do that, right? He's holding them there. And he's done some work to take them there. Now this picture of a man holding balls up, waiting for a pipe to someday come so that he can begin his current below, after which he can start doing his whole job. is our cell. Because now, if we draw out what looks like a typical cell around this, and if we name the man inside, chemical X, now something chemical is happening, we can't tell you more right now. And then, if we tell you, instead of holding up tennis balls, this whole thing over there, those balls that he's holding up are smaller than even water balls, smaller than even air balls. They are balls that are extremely small, probably the smallest balls we know, called electrons. Now, what these electrons are and all that and all, we'll learn later, okay? Then what if I tell you everything now, what you do in 7th, 8th, 9th, 10th and all? So that we'll learn later. So that was like a few minutes, right? And you already learned so much. If you want to learn much more, download the Byju's Learning app. We made hours and hours and hours of content just for you to learn. Hope to see you there.